Hello everyone, this is Krishna Chaitanya, Associate Professor from Department of EEE. So today would like to discuss characteristics of DC motors. What is the significance of characteristics of DC motors is to be discussed first. So by looking at the characteristic of any DC motor, for that matter for any machine, so we could understand the behavior of the machine as any one parameter is changing, how the other parameter is changing along, right? So by looking at the characteristic, the plot between any two parameters in any machine, we could understand that what is the behavior of one parameter change with respect to other parameter. So likewise, there are three prime important characteristics that need to be drawn for the DC motor. So they are speed current characteristic, torque current characteristic, speed torque characteristic. So we'll see how these characteristics will look like and what are the guiding dynamic equations that will help us to draw the characteristics, each and every characteristic of DC motor. And also we also draw these three characteristics for different DC motors. So as we know, we have DC shunt motor, DC series motor, and DC compound motor. We'll see how the characteristic will look like in case of each and every motor, shunt, series, and compound motor. So one more application, one more significance of this characteristic is by looking at the characteristic, the plot of the characteristic, we can identify whether a particular application, whether a particular motor is suitable for a particular application or not. So suppose we have a motor that is to be used in case of hoist applications. So for a motor is needed to be used in case of a lift application. So in case of a conveyor belt application. So all these applications actually need the characteristic to understand. So by looking at the characteristic, we can find the right application of a particular motor. So such is the significance of these characteristics. So we'll see each and every characteristic, speed versus current, torque versus current, and speed versus torque for DC shunt motor first, and then series, and then the compound respectively. First, in case of shunt motor, as we all know, the shunt motor so this is the schematic of shunt motor. This is shunt field resistance and this is armature. RSH is the shunt field resistance and RA is armature resistance. So VT is my terminal voltage, IA is armature current, and ISH is shunt field current. IL is the line current. Right? So before moving on to the characteristics, so we need to derive the dynamic equations that help us for drawing the characteristic. So let us see what are the dynamic equations that will help us for drawing the characteristic. So first one, we all know that the terminal voltage of DC motor is equal to back EMF EB plus armature resistance drop IA RA. And also in case of shunt motor, the field winding, the shunt field winding is receiving the constant voltage VT. So we can say that the shunt field current ISH can be written as VT by RSH. Whereas RSH is the shunt field resistance, VT is the terminal voltage, ISH is shunt field current. Since the terminal voltage is directly applied across our shunt field winding, the current passing to the shunt field winding can be written as ISH is equal to VT by RSH. Since terminal voltage is always constant, and as shunt field resistance is also constant, I can say that the ratio of VT by RSH, which is our shunt field current, is also constant. So ISH is constant, and the one who is creating the magnetic field or generating the magnetic field, ISH is constant. Since ISH is constant, phi SH is also constant. So the flux phi SH in shunt motor is constant. And then we'll follow this expression the basic expression Vt is equal to Eb plus IRA. So one more thing would like to address is we need to draw these three characteristics. First one is N versus IA and T versus IA and N versus T. So before drawing the characteristics between these particular two components or two parameters, so we need to get a relationship between these two. So these guiding expressions, the dynamic expressions, will help us to draw the characteristic between these two particular components or parameters, right? So let us get a relationship between N versus Ia, and then it is easy for us to draw the characteristic. So N versus Ia. So to get the relationship between N versus Ia, so we have the basic equation Vt is equal to Eb plus IRA, and I'll arrive at Eb is equal to, from the expression 1, I can write Eb is equal to Vt minus IRA. You can write this is expression 2. At the same time, I can find the expression for Eb. I can write the expression for Eb. Eb is equal to phi Zn by 60 into P by A. This is expression for Eb, right? As we have expression for Eb is equal to, in terms of flux, number of conductors, speed, number of poles, and number of armature parallel paths. I'll write all those parameters which are constant and all those parameters which are variable separately, right? So since Z is a constant parameter, I'll write Z. P is a constant parameter. Since P is a number of poles, it's always a constant. And 60 is a number. And also A, the number of armature parallel paths, is also a constant, which is a number, a constant number, into phi N. Actually, phi is also constant in case of a shunt motor, but at higher values of armature current, the armature reaction persists, and there will be a little change in magnetic flux in shunt motor. So I wrote the shunt motor flux separately, even though it is constant for most of the time. Right? And let us write this N. Actually, N is measured or represented in RPM, and I am expressing it in case of radians per second. So while discussing or plotting the characteristic equations or characteristics for any of the motor, so it is better to express the speed in case of radians per second. So I'll show you the reason why I'm expressing the speed in case of radians per second instead of RPM, right? So better express our speed in case of radians per second. To convert the speed in RPM to radians per second, we need to multiply it with 2 pi and divide it by with 60, right? So 2 pi N by 60 is your angular speed in radians per second, measured in radians per second, right? So N is expressed in RPM here, and N is expressed in case of radians per second, which is nothing but angular speed represented by omega. So I'm rewriting the same expression, Zp by 60A phi. So to express N in terms of omega, I need to multiply it with 2 pi by 60 and 60 by 2 pi. So this expression doesn't change. Just I'm multiplying my speed N with 2 pi by 60 and 60 by 2 pi. There will be no change in the expression. But 2 pi by 60 into N can be written as our angular speed omega. So I'm rewriting the same expression, Zp by 60A into phi omega into 60 by 2 pi. So the 60 over here and 60 over here will get cancelled. So we got Zp by 2 pi A into phi omega. So now I am writing this Zp by 2 pi A as K, Zp by 2 pi A as K. I'm substituting the value of K over here. So K phi omega. This is our expression for back EMF, which was simplified and written in terms of shunt field magnetic flux phi and also angular speed omega. All those terms which are constant are written with a variable k, with a letter k, which is nothing but Zp by 2 pi. And coming to the next expression for the EB, the first expression what we have written for EB is equal to Vt minus IARA. Let us substitute the expression what we got for EB in terms of flux, speed and k. We will substitute here. So we'll get k phi omega is equal to Vt minus Ia into Ra. So from this, omega can be written as Vt by k phi minus Ia Ra by k phi. So we arrive at an expression between speed omega and current Ia, angular speed omega in radians per second and the current Ia. So as I told you that we need to get that dynamic relation between these two parameters where the characteristic exists, where the characteristics needs to plot, right? So since the first characteristic is between omega and Ia, I mean speed current characteristic, we have the relation between speed and current here, right? So now we'll see the speed current characteristic as we have the dynamic relation, dynamic equation between speed and current. So which was omega is equal to Vt by k phi minus Ia Ra by k phi. Right. So taking armature current in x-axis and speed in y-axis. So we'll keep on changing the value of armature current from no load to full load. We'll see how the machine speed will change from no load to full. Right? So at no load, Ia is very small because as Ia completely depends upon the load. If there is no load, Ia will be very small. If there is load, the Ia will be increased. So at no load, Ia is very small. So IARA drop is also very small. Since Ia is very small, IARA drop is very small. IARA drop is very small. Then we can neglect the IARA drop as it is very small since at no load. So we'll find what is the speed at no load. Omega is equal to Vt by k phi. So I'm neglecting the drop IARA by k phi. So the term IARA by k phi can be neglected conveniently. So now this is my expression of my speed at no load. So since it is the no load speed, I can name it as omega naught. Omega naught is the value of speed at no load. Right? So since at no load Ia is conveniently neglected, almost zero, and at no load the corresponding speed is omega naught. This is omega naught. So the characteristic starts from y-axis, on the y-axis at a value of omega naught. Now as I keep on changing the value of load, that means if the motor is loaded continuously, eventually armature current increases because to drive the increased mechanical load, the motor has to draw more amount of armature current from the source. So this increased armature current eventually leads to more IARA drop. So what happens to my speed if the load is increased eventually? So as the IARA drop is keep on increasing, the speed will reduces. As we are looking at the expression, it is on the second term which is subtracting or deducting the value of IARA by KFI. So as the load is increased, IA increases and eventually IARA also increases. So if IARA increases, obviously the speed will start decreasing. So this can be observed in the characteristic. This is how the speed should look like if there is a constant value of it. So since with the increasing load, the armature current increases and also the speed decreases. This is how it looks like. The armature current, the drop in armature current will also very small. So definitely IARA, the increase in current increases IARA and eventually speed decreases. But the value of IARA is pretty small because the term IARA divided by K phi still has a small value. So the reduction in speed will be very small. Right? So as we can see here, the difference between the no load speed and the actual speed of the motor, if it is loaded, is very small. Then at full load or the rated load, so when IA is reached to a value of full load or rated load, that means when IA is equal to I full load, higher values of the armature current, so the armature reaction sets in. Actually, as we know that the armature reaction is the effect of armature flux on the main field flux. So till now, I mean to say till this point where the armature current is on the way of reaching its final value or full load value, the armature current has no significant impact on the main field flux. The armature flux has no significant impact on the main field flux. So the armature reaction is eventually not so significant and not so effective. But once when the load is reached to its final value or full load value, the armature current is pretty higher than its natural value, and then the armature reaction increases, and the effect of armature reaction, which is demagnetizing in nature, will reduces the main field flux. So at higher values of armature current or higher values of the load, the armature reaction sets in, and its actual effect, which is demagnetizing effect, will reduces the main field flux. So from this point, the main field flux decreases. Main field flux decreases. So if you look at the expression here, Vt by K phi minus IARA by K phi. So here IARA is increasing, but K phi by the value of flux is decreasing because of the armature reaction and also the saturation of the rotor core, because until a particular value of magnetic field, the armature core will not get saturated. But once at a particular value of armature current, the armature core will get saturated, and also because of this, another reason, the value of flux phi will get reduced. So here, if you look at this expression, IARA is increasing and phi is decreasing. So what will happen to my parameter? This second parameter, the second term, will it increase or decrease? Because the numerator tends to increase the value, whereas denominator tends to decrease the value. Right? So both the numerator and denominator tends to increase the second term, because numerator is increasing. If the denominator is decreasing, also this entire term will get increased more rapidly than the IARA is increased alone. So the drop in speed will be more pronounced or rapid once the armature reaction sets in. So until this point, you may observe very little difference between the no load speed and actual speed. From that point where the armature current reaches the full load current, where the armature reaction starts, obviously we'll find more dip in the motor speed. So what happens to my characteristic if the armature reaction is completely neglected? If armature reaction is completely neglected, as we keep on increasing the load, the current increases, IARA drop increases, and eventually the motor characteristic will be an extension to it like this. So this line, which was extended with dotted line, is the speed with armature reaction neglected. Whereas this is the speed with armature reaction. So we can see that the speed current characteristic of a decision motor is almost a straight line till at a point where armature reaction sets in, or armature reaction has started its significance effect of demagnetizing nature. So as we can observe, the characteristic is almost a straight line, which was not at all completely deviated from its no load speed. Almost a little difference between the no load speed. So we can say that a shunt motor without armature reaction, or until the maximum rated load is reached, almost is having a constant speed. So we can also call the shunt motor as a constant speed motor. This is the reason why it was popularly known as constant speed motor. There is no deviation between the no load speed with the actual speed when the load is increased. Right? So this is about the speed current characteristic for a decision motor. So we'll see how the torque current characteristic looks like. So second one, the torque current characteristic. Again, to plot the characteristic between torque and current, we need to get the dynamic equation between torque and current. How to get the torque and current equation? So we have the torque expression of T is equal to, or let us write the output power expression for a DC motor, right? So the mechanical power which is being converted into the electrical power which is being converted into mechanical power is EBIA. EBIA is the electrical equivalent of mechanical power developed, where EV is the back EMF, I is the armature current. So this part of electrical power which was received from the source is being converted into mechanical power. And what about the mechanical power expression? Mechanical power expression is equal to 2 pi n by 16 to torque. You can also write it as omega into t omega. But since this is the mechanical power being converted and this is the mechanical power that was converted, so these two are equal. This is the actual electrical equivalent of mechanical power converted. So I can also write this as electrical equivalent of mechanical power developed. It's an electrical equivalent. All the terms of electrical in nature. What about this expression? This expression is the mechanical power convert developed in terms of mechanical terms. Speed, I mean to say omega, and torque, mechanical torque. So these two are equal. This is EB IA and omega t. But our aim is to get a relationship between Vs, T and IA. So if you write K phi omega in place of EB, as we have already derived it, into IA is equal to omega t. From this I can write torque T is equal to, as you can get cancel omega in here over there on the left hand side, right hand side, I can write K phi IA. So this is the expression for torque in terms of armature current. So here K, what we have shown here, and also the K, what I have shown in case of EB, is both are one and the same, right? Now, since we have the relationship between torque and armature current, let us draw the characteristic of torque versus IA. Again, we need to keep on change the armature current from no load to full load without armature reaction. And once the armature reaction sets in, we will see how the torque current characteristic changes. So we got the relation T is equal to K phi IA, taking armature current in the x-axis and torque in the y-axis. Taking armature current in the x-axis and torque in the y-axis. So as we observe that phi is constant in case of shunt motor, as we see that phi is constant in case of shunt motor. So if you keep on increasing the armature current from no load, IA increases, and also eventually torque also increases linearly, since I have a direct relationship between torque and armature current. So as IA is increased, torque is also increased. But as we discussed in case of speed current characteristic, this happens. This relationship between linear relationship between torque and current will be continued until the armature reaction sets in. Right. So at this point, let us say the armature current is reached its value of full load value. So at full load value of armature current, armature reaction starts its demagnetizing effect, and as a consequence of armature reaction, when IA is equal to I full load, armature reaction demagnetizes main field flux phi. Demagnetizes the main field flux phi. So this relationship between T directly proportional to phi A no longer valid. So as your load is telling your armature current to increase, but the armature reaction is telling your main field flux to decrease. So the net effect of torque will be not a straight line. Obviously, the torque will increase, but it won't increase in respect to or in line with your armature, not linear with armature current, but it will be deviating from its actual straight line characteristic and tend to change from its linear behavior. Right? This is torque with armature reaction, and this is actual torque. Sorry, this is the torque without armature reaction. This is torque without armature reaction, and this is the actual torque with armature reaction. And this is the second characteristic. And the last one, the third characteristic, speed versus torque. Again, to plot this speed versus torque characteristic, we need to get the dynamic equation between N and T. Again, we start with this expression. EV is equal to Vt minus IARA, and also EV is equal to K phi omega, and also T is equal to K phi IA. All these expressions are what we have derived till now. And since I have IA, I need to get a relationship between N and T. So let us substitute N, I mean sense in the sense N or omega, either in RPM or angular speed. So preferably angular speed, because I'm dealing with characteristics. It is better to have N speed expressed in angular speed measured in radians per second. Right. So and also let us substitute this value of EB K phi omega over here, and I need to have this expression in terms of torque, because I need to find the relationship between omega and torque. So let us have IA torque here instead of IA. So since from this relationship I can get IA is equal to T by K phi. So if you substitute these two values in the expression, one will get K phi omega is equal to Vt minus, instead of IA I'll write T by K phi and RA. So if you write the expression for speed, omega is equal to Vt by K phi minus P by K phi whole square into I. So this is the expression between speed and torque. Now we'll see how speed changes with respect to torque. Again, we need to change the value of torque from no load till it reaches the full load value. We'll see without the armature reaction how the speed will change, and also with armature reaction how the speed will change from no load to full load. Taking torque in x-axis and speed in y-axis. Taking torque in x-axis and speed in y-axis. Let us see what happens to our torque when there is a no load. So as we discussed that when there is no load, the IA value is pretty small, as so the value of torque. So we can neglect the second term T by K phi square into RA when there is no load on the motor. So the motor will start from it, the characteristic will start from its no load speed, where its value equal to omega naught is equal to Vt by K phi. So it also starts with its no load speed, which is written as omega naught, nothing but Vt by K. And as we keep on changing the value of load, current IA increases, motor current IA increases, eventually torque also increases, the second term increases, so the speed value decreases. This is the constant value of speed. I'm writing it for reference, I'm drawing it for reference. So machine speed decreases with respect to torque. Again, this happens till we reached a full load value. Whenever the load reaches the full load value, current will be pretty higher and torque is higher. Eventually, the armature current starts a significant effect of demagnetizing in nature. So the main field flux will decrease. So when the armature reaction sets in, the armature reaction demagnetizes the main field flux. So flux phi also decreases. So till that point, we treated main field flux phi as a constant value, but then we need to consider the value is decreasing from there on. So what is happening here? So the torque is increasing as we keep on increasing the load, and the main field flux is decreasing as armature reaction is increased or demagnetizing the main field flux. So eventually the second term will be more rapidly reduced from that full load point. So we can observe, let us draw this characteristic again. So from here on, we can find the characteristic is decreased rapidly than it is without the armature reaction, right? So to some extent, not to some extent, actually it looks like the characteristic of speed and armature current. And what happens to my characteristic when there is no armature reaction? Eventually it is the extension of the initial characteristic. So this is speed without armature reaction, and this is speed with armature reaction. So now we have seen three characteristics: speed current, torque current, and speed torque characteristic of DC motor. We will see the remaining characteristics in the next class.